Hi, welcome to Module 2 of Lecture 13. In this module, we're going to talk about partial derivatives. Now, this isn't the first time we discussed partial derivatives. We talked about them way back when we first discussed the derivative in one dimension in our lectures on calculus. But again, I'm not going to assume that you remember all that stuff. We're going to start from the beginning basically here. Now, a partial derivative can be written like this. If the function is f, and let's say the function has three variables, and the partial derivative with respect to x would look like this. You also sometimes see this notation, the older notation here. We mentioned this way back again when we discussed calculus in the first place, when we talked about notation. Basically, the goal of a partial derivative notation-wise is to tell you which variable you're taking the derivative relative to. So we called the definition of a derivative in one dimension was this, that limit. We did a whole bunch of examples of this way back in part 2 of the course. And again, if you haven't done any derivative stuff, don't watch this video right now. Go back and make sure you understand how to take a derivative in one dimension first. I'm assuming you do for the rest of these videos. Okay, these lectures. So for more than one dimension, it turns out it's more or less the same thing. So this would be the total derivative in one dimension, which is the same as the partial derivative in this case. But let's say you had more than one dimension. Let's say f were a function of x, y, and z. Well, it would be the exact same definition. You just keep y and z constant. And this would be the partial of f with respect to x. And again, that sort of curly d kind of thing is read as partial. The partial of f with respect to x, or the partial derivative of f with respect to x. That's it. So fundamentally, you calculate a partial derivative by taking the derivative, as we did before, with all the exact same rules, with respect to a particular variable. And the key is you keep all the other variables constant. That's the key. It's the same as a normal derivative that you've seen before, except you keep all the other variables constant. Before in one dimension, there were no other variables, so effectively you were keeping them constant. They just weren't there. For a partial derivative, you keep all the other variables constant and take the derivative with respect only to the variable in question, to the variable you're taking the derivative with respect to. That's it. That's all there is to this. That's the whole definition of the partial derivative. There's nothing more complex, and we can see pretty quickly how this works with some examples. And again, I'm going to go through this pretty quickly because I've assumed you've gone through and done a whole bunch of problem sets on taking derivatives in one dimension, and so maybe this won't be you won't remember this as well as you might like to, but you can go back and check out the stuff you did before. Again, you can always pause these videos. But here's some examples. Let's say you have a function in three variables here. And let's say the function is x, y, z plus x squared over z minus y, let's say z squared. There you go. There's a random example. There are more examples in the book too. What's the partial derivative of f with respect to x? Well, you take the derivative of that function with respect to x, holding everything else constant. So the first term is linear in x. The derivative of x is 1. Y and z here are just constants. So you have a constant times 1 versus yz times 1. Second one. Now this is complicated. X squared over z seems complicated. However, z is a constant here for this partial derivative. So it's just the derivative of x squared times this constant 1 over z. We can put this out front. The derivative of x squared is 2x. What about the third term? It has no x in it. Therefore, you could treat x as a constant there just as 1. The derivative of a constant is 0. So even though there's a y and a z here, since they're treated as constants, you're really taking the derivative of 1 effectively. And 1, the derivative of 1 is 0. So this term goes away completely. And this is the partial derivative of f with respect to x. As you see, It was in fact no more complicated than taking the total derivative in one dimension. You do the exact same procedure. The only difference is you must remember that all other variables are held constant. And just to be complete here, we can go through and do the rest of this example. Here the constant is xz, and the derivative of y is just 1. In the second term, there is no y. So you have the constant x squared over z times the derivative of 1, which is 0. And the last term, you have a constant, negative z squared, times the derivative of y again, which is just 1. That's it. So this thing goes away, and you have xz minus z squared. And finally, the very last one, the constant in the first place is xy now, and the derivative of z is just 1. Now here, the constant is x squared. The derivative of 1 over z, remember, is negative 1 over z squared. If you remember that 1 over z is z to the negative 1. So you pull down the negative 1 out front. That gives you that negative 1 right here. And then you subtract 1 from the exponent. Negative 1 minus 1 is negative 2. And z to the negative 2 is the same as 1 over z squared. So that's this term. And this last one over here, the constant is negative y. The derivative of z squared is 2z. And this one actually is all three terms. But that's it. We just calculated three partial derivatives with respect to x, y, and z of this function of three variables. That's all there is to this. So practically, functionally, a partial derivative is the exact same in terms of how you calculate it as the derivative in one dimension. All you're doing is taking the derivative with respect to that one variable, holding every other variable constant. That's it. Okay. So what else can we do with this? Well, lots of stuff, and we'll see for the whole rest of this. I think every single thing that comes after this, with respect to the next module, will involve centrally partial derivatives. So it's going to pop up in a whole bunch of cases for optimization, for implicit differentiation. All this stuff would be central. We'll get to all that soon enough, though. For now, I want to focus on some more empirical topics, because the reason you'll be listening to this lecture, separately from the other lectures that come later on in this part of the course, is that it contains, as we said in the first module, it contains important information for you starting off in social science methodology and stuff. So, what is that information? Well, consider the basic linear model, linear regression model, right? You have some dependent variable y, and you have some independent variable x1, right? That's where we started before. We really considered only one variable. But remember, back when we did in the previous part of the course, when we did matrices, we created a matrix X that contained a whole lot of variables, right? More than one independent variable. We can write that outside of a matrix like this. So this would be a dependent variable y that's a function of three different independent variables, x1, x2, and x3, in a linear fashion. And here's the error term. Now remember, the partial derivative of y with respect to x1 is by definition the derivative of y with respect to x1 holding all other variables constant. Now, what does that mean? Let's go back to the intuition behind the derivative in the first place. Well, derivative was the marginal rate of change in one variable with respect to another variable. So here, partial y partial x1 is the marginal rate of change in y with respect to x1 holding all other variables constant. And that's the key there. It's the marginal rate of change in y with respect to x1 holding x2 and x3 constant. What is in this case? Well, if you hold them constant, this is a constant and this is a constant, so those derivatives are 0. The only derivative here is this one. x1 is linear. Its derivative is 1. So therefore, partial y partial x1 is just beta 1. And the importance of this is it gives you a clean interpretation for the meaning of the coefficient on the independent variable. Beta 1, the coefficient on the independent variable x1, is defined as the marginal rate of change in the dependent variable y with respect to the independent variable x1 holding all other variables in your regression model constant. Let me say that again. Beta 1 is the marginal rate of change in the dependent variable y with respect to the independent variable x1, holding all other independent variables in your model, here x2 and x3, constant. Note, it does not hold variables you don't consider in your model constant. It only holds constant the variables that you consider in your linear model. And that is the primary use of the partial derivative that you encounter as an empirical, political, or social scientist. It tells you, it gives you the proper interpretation of the coefficients on your independent variables. Even though it's not always mentioned in this context in stats books, this is what it means. And this is why it's very useful to understand for stats what the partial derivative is, because it gives you the meaning for your coefficient. Now, this point you might be saying, that's great, but why do I care that much about this? I mean, I can just be told, I can just remember that it's a marginal rate of change. Why am I supposed to take a derivative? Here's why. Let's consider a slightly more complicated linear model. So here we have beta 1 x1 plus beta 2 x2. But now instead of an x3, let's consider what's called an interaction term. We've looked at this before too, but it's worthwhile mentioning it again. And there's the error term. What now is the marginal rate of change of y with respect to x1? It's a little different. Still the beta 1 from this term over here. This term still differentiates to 0. What about this term? Now there's an x1 here. The derivative of x1 is just 1. What's the constant multiplying it? Well, it's the coefficient on that term multiplied by x2, because we're treating x2 as a constant. So now we see explicitly that the marginal rate of change of y with respect to x1 is equal to the coefficient on 1 plus the coefficient on the interaction term times the value of the second independent variable. Therefore, the marginal rate of change of the dependent variable y with respect to x1 actually varies with the value of the second variable. So when you're trying to understand, for instance, whether or not you have a significant result for the effect of x1, this effect can vary. If you're interested in the marginal rate of change, which you are, it's not just beta 1, it's beta 1 times beta 3 times x2. So if this is x2 on this axis here, then you might find that the marginal rate of change, this thing, which is the actual thing of interest, not beta 1, this is the thing of interest right here, because you want to know the marginal rate of change of y with respect to x1. This might start off positive and get smaller over time. And if these are the errors on this, it might be significantly different from 0 over here, but not when x2 is high. So these people call interaction plots, and these are ways of understanding how the marginal rate of change of an independent variable changes with values of another independent variable to help you understand when the first variable is actually having an effect. This picture here in the lower right-hand corner of this screen might represent the case in which when x2 is low, x1 has a strong positive marginal effect on y, but when x2 is high, you no longer see a significant marginal effect of x1 on y. So it's a more complex story, and it helps you understand better how y is changing with x1 in a more complicated case in which x1 and x2 might be complements or substitutes in their effect on y. And you learn a lot more about this in your stats classes. But without understanding how you get the marginal rate of change in y with respect to x1 from the equation using a partial derivative, you can't actually understand how to interpret your interaction effects properly. So that's one reason why it's important to really understand the partial derivatives beyond just memorizing that beta 1 is a marginal effect, because it's not always a marginal effect. It's the marginal effect when you have no interaction terms and nothing of higher order. But when you have a more complicated model, as you often have, the partial derivative is the marginal effect of y with respect to x1 or x2 or x3. Okay, really quickly, one more example of this. Let's say you had a model that looked like this, that's no longer linear, in which now you had not only the linear term, x1, but also a quadratic term. You might see this when you believe that the marginal rate of change in y is actually itself increasing in the variable. So that's some kind of curvature in the relationship. What's the partial derivative here? Well, this the first term as before. The second term now is the derivative of x1 squared, which is 2x1. So we have beta 2 times 2x1, meaning that the actual marginal effect is beta 1 plus 2 beta 2 x1. And again, the marginal effect is actually increasing in the value of x1 if beta 2 is positive, or decreasing in the value of x1 if beta 2 is negative. So you can get more complicated effects by using nonlinear models here. And the important thing to recognize is that you can still use the partial derivative to understand what the marginal effect is, even for more complicated models than a linear one, thereby again showing the importance of understanding what the partial derivative is and what it means, and how it can be used to properly interpret your regression models. So before ending, I want to mention one last thing, the concept of an elasticity. All these partial derivatives are marginal rates of one variable with respect to another variable. Sometimes you might want relative changes instead of absolute changes. So the change in one variable relative to its value with respect to another variable relative to its value. We can define an elasticity that looks like this. This should be the elasticity of y with respect to x, which gives you relative changes. Why are these relative changes? Well, you can write this a little differently if you want to. This is a little abuse notation, but you can see the point. The point is, on the top you have the infinitesimal partial y divided by y, so it's the relative value of that change relative to the value of the variable y. And in the denominator you have the relative change of the change in x with respect to the value of x. So these are sort of relative changes. You often see this sometimes written like this because the derivative of the natural log is 1 over the variable. You can often write this like this. So these are the elasticities, and this is another way in which you see partial derivatives. Typically in economics, we can try to understand, say, the price elasticity, but you see it sometimes in political science as well. That's it. That's the end of this module. In the next module, which is the last of this lecture, we'll discuss multiple integration in the context of probability distributions over more than one variable. Thank you very much.